Good morning. Today we start learning some recursion. And before we start, I would like to say some useful information. First, you need to know that next week will be the Easter holiday, and during this, I don't stream anything. But also, you need to know that after this holiday day, you should prepare for the next course for first programming practice, and I will add some information into Moodle course at the top of the course, and you will find a link, or later I will send an email with invitation to Microsoft Teams, because I need to introduce to this course. And when this starting, you should create some software like 4 tasks and simple projects, I think, or I'm not sure, maybe the quiz also. And later I will add some information and send email, and you need to join to this group, and later after those holidays we have some live talk using the voice chat. And after this, now we moving into our today topic. Today topic is, as you see here, it's nice structure like in drawing world, in graphics world. Maybe in some video games you also sometimes you see this set. It's Mandelbrot set. It's fractal. Fractals is really around us. You will see the trees, snow, snowflakes, and a lot of other nice structure, which is looks like a recursion. And the recursion idea is to solve the huge problem, to divide into the smaller problems, and when this problem is small enough, you're able to solve this problem. And for your tasks, there is the task 4. You need to solve your factorial, Fibonacci sequence, binary tree, because binary tree it's itself recursive structure, because as you see, you need to move deeper and deeper, and when you're backing, moving to the next branches. And here also there is Ackermann function, and here is the first, as you see in the Linux or any operating system, Unix, not Linux operating system, you will find the file system. File system is also, it's like a tree structure, and if you met the trees always will be, maybe sometimes you're using the iterative or forward thinking way, but much easier to solve the problem to read recursively using recursion. And this task is also using the recursion here. And before, I also added to the tree implementation. I already show the recursive way, but the recursion usage also for a lot of tasks, like for sorting algorithms, because if you have the tree data structure, you need to use the recursion. It's better approach, and sometimes you need to get the best complexity or asymptotic notation, like big O notation, for example, to get the best results. And I'm just introduced to the basic what does it is recursion, but I now move in more details and show what is really that recursion, because recursion is it's not a huge difference between the iterative way, is only your brain thinking in different way, and some programming languages before start using, like when you have some programming languages, some languages doesn't have the loops, and if it doesn't have the loop, there is no chance to solve the problem writing the hard-coded code if you hard coding. And for that reason, in some programming languages is use recursion. And this technique, of course, use a lot of memory. And if you're using the recursion in wrong way, you will get some stack overflow. And later we will see when you able to get it. And now I would like to start our lecture notes. And first we'll look into understanding of recursion. Recursive programs is one that calls itself one or more times with each execution until it satisfies the base case arguments. And discontinues calling itself. And you need to know to understand the base case, recursive case, and pattern of convergence. Base case, it's always sometimes when you have, I don't know, maybe I try, if you have some loop, here loop, you will always have some condition like e, I don't know, e less 6, for example. And the base case, when you have the base case in without a loop, you need to write some correct condition to stop this recursive call, because the recursive functions calling itself like infinity times. And if you not added the base case, you will get you will stuck in infinity loop. And when you're stuck in infinity loop, when you're using not a loop but recursion, you get stack overflow 100%, because it's it's storing all function callings in the stack, and stack will stack overflow. And recursive case, it's always, or when you have some function and calling itself, like any type of function, we later see what this is. You're just calling it the same function infinity time amounts till the base case it happens. And later we see the real example, much easier to understand what is base case, what is recursive case. And of course you need to have some convergence, the result converge to the final aim to solve the problem. Because if your problem is not convergence, it's really bad practice. And now we need to delete this, sorry. The types of recursion, there is the two types. Of course, in the internet or online, you're able to find the more types, and today we look into more subtypes of linear and non-linear types. Like linear type, it's one of frequently used because you calling function itself in recursive case, like you're calling itself anytime amount. It's similar to the loop, like looping itself, and for example reducing some value by 1, for example. And nonlinear, it's really complicated structures. And if you have the nonlinear recursive functions, today I will show how to break your program using only the small integers, like passing 2 parameters, 2 arguments, and to break your program, because it's not possible to calculate. Not enough the memory, or if enough memory, it take a lot of time to calculate your result. And those 2 types, it's really easy to remember, the linear and nonlinear. And there is subtypes. Later we see subtypes of linear and nonlinear and different examples. And now that I just would like to say in more details the base case, what this means. And base case means the method does not need to recursively call itself anymore. When you need to stop, like when you have the loop, you need to stop. Here is the same approach using base case, and it returns the default value or nothing. You need to decide you're returning something or you just stopping at the bottommost activity. Recursive case occurs when the method cannot resolve the problem without a recursive call to itself. The recursion always will work in a recursive case, because you need to call itself till the problem solve or till the base case happen. And convergence means that you recursively call the method until you reach the base case. And if you have, for example, n integer, and you dividing by 2, and this result not approaching to the base case, it's wrong convergence, and you will get really waste of memory. And of course, convergence should always happen, because you need to reach the base case. If you're not reaching the base case using recursion function, it's really bad practice. And the recursion process, when you have 2 different thinkings, like recursion looks backward through the chain events, traditional loops look forward through the events. The difference between those, as you see here, is loop have the forward thinking, and as you see 2 problems, and recursion works backward through the convergence base case to the base case, where the base case occurs when you are back to the beginning. Later I will show the example, you understand how it really works. It's really filling the stack, and when you implementing easier to implement using recursion, that doesn't mean it's really effective to use it. But if you have a lot of amount of memory, sometimes it's really good practice to use the recursion. And here, as you see, process adding number to itself, and given t1 equals 5, and then we just the first iteration have 5, after that plus 5 it's 10, plus 5 it's 15, and till the n. Like if we picking the n equals 3, we get 15 result. If you have the recursion, you thinking different. You subtracting the number from itself. First you have, for example, n equals 3, or just n equals 3. You just subtracting. 3 minus 1, 2 minus 1, 1 minus 1, like this. It's different approach. Like here it's appending. When you have the loop where you just adding 1 plus 1 plus 1, because you need n equals 3, 1 plus 1 plus 1, and after this iterating I value, you just adding the 5 plus 5 plus 5. And here you have different approach, and we later see how it works, the recursion. And you get 15, 10, and 5. And here, as you see, there is forward thinking, or here is backward thinking. It's like from the top to the bottom. Yeah, different thinking. And this thinking, it's you able to say that forward thinking and backward thinking, or just when you have the recursion or iterative loops. And now we moving to the next slide. And here, of course, the bad practice when using recursion, if the base case is poorly chosen, of algorithm does not converge to the base on the base case, the process running on the computer will quickly run out of memory. You will get the stack overflow. It's like if you, no, maybe I need to write a bit, picking like values, double value, I don't know, double n equals 5, and each iterations n minus, for example, 0, 0, 0, 0, 0, 1. And if each iteration you calling this result, you calling function itself and reducing the n with that small constant value, you will never reach the base case and you will get the stack overflow memory. And when you're creating the recursive functions, you need to think. You need to think before you do something. Okay, forward and recursive sequences. Forward thinking is the loop method, is a more traditional method of solving problems. There is a lot of problems which you're able to solve using the forward thinking. And there is some problems like some sorting, searching, trees, file systems, etc. You need to use recursive thinking or backward thinking. And creating the method does all the process and return the value back calling the method. What does it mean? When you thinking in this process, for example, you will have this, you will have the base calculation here. And for that calculation, you just calling the function once. Oh, I need to change the marker, sorry. You're calling the function once, and here you calculating your result. Result plus equals 5, of course. And as you see before, we adding 5 plus 5. First you have 5. Second iteration you have 10. Third iteration you have 15. Fourth iteration you have 20. Fifth iteration you have 25. And You just adding the number. It's really easier to think in that way and to calculate the sum of sum up some numbers, or sum up some constant value like 5, if you have n equals 5, and you calling once this function. When you have the recursion, we see different approach. And here I will move to the next slide. And if you have the backward thinking, the recursive method shown demonstrates how the recursion works with backward continually calling itself until the base case reached. Okay, now I would like to introduce how it works. You have the function. For example, we have n equals 3. I don't take the huge numbers because it's easier to explain. And here is a base case. If n equals less than equals 1, you're returning the number, like we're returning 5. Base case happens when the n it's less or equals 1. And how it's happen, how to approach or converge to this base case, you need to call itself function here. Backward thinking, and as you see here, n minus 1. And you're calling, reducing the n value by 1. If you're picking the 3, you minus 1, first iteration. And first call will be the 3, next call will be 2, and later will be the 1. And you call this function itself. And if you say that there is a backward thinking, I will take different maybe color, the red one. Here you need to think like this, not from the top, like forward thinking. You need from the bottom, because you need to calculate. And I make the shortcut, like here, that function I call as a b. Change the letters because it's easier to write. For example, have b, and you're passing 3, of course. If you're passing the 3, we calling the function b 3 minus 1 is equals to plus number. Next call will be b calling 2. We calling this b2 because it's not solved this problem. You need to move to the base case. When is b equals 2, you're calling b, b here n minus 1, n is equals 2. I need to write like n equals 3, n equals 2. And when n equals 2, 2 minus 1, it's 1. Plus number. Okay. If n equals or less, n equals 1, we calling b1. B1, as you see, is base case, it's returning 5. And as you see here, we adding to the stack. Here is a stack. Just I need to maybe change color. Here is a stack, bottom element or the first element, another element, and the last one element. And you need to think that when you're creating the recursion functions, you always will adding this function calls into the stack. And when you reaching the base case, you start popping out, pop, or remove from the stack. B1 equals 5. You just, if instead of B1, adding 5. 5 plus 5 equals 10. Because number we know, yes, 5 is here. Here we get the 5 and we popping this number, and of course we don't have in the stack those two elements. We adding this element here like 10. 10 plus 5 is 15. And the later we just removing from the stack everything, and we will have the 15 returning value. And here is a difference between the forward thinking, backward thinking when you have recursion. First you dividing into the small problems. It's like in divide and conquer paradigm. You just calling itself, getting the base case or returning some value, and you just moving and adding this value down, and you get the result 15. As you see, of course, it takes a lot of memory because you store in the stack everything. Okay, now we're moving forward, and here I write in the table because first I need to explain, and later when you're reading the slides, if you're reading the slides, it's easier to understand how it works. Like you have backward thinking, you have recursion, and the call stack here is called stack, and current step, that means you need to look from the bottom. Current step. First you backward thinking, calling backward 5, 4 plus number, 4 plus number, if you have n equals 5. 3 number is the same like I also showed in the some example, n equals 3. And when you get the number, you moving back down below, you will get 5, 10, 15, 20, 25. We're just calculating this result. Okay, and linear recursive function is a function that only makes a single call to itself each time the function runs. Of course, would call itself multiple times during its execution. The factorial function is a good example of linear recursion. And here is also linear recursion because you're calling itself only once and every iteration multiple times. There is a tail recursive function. There is no factorial. There is no factorial added here. We write some code then. Sorry, if linear factorial function is a good example of linear execution. We just create new project. Recursion samples, and we need to create a factorial. Calculating factorial, we just create int factorial, and we have the n as always. And when you're using the forward thinking, maybe I create the two different approaches. Forward thinking, maybe I create F forward thinking, and we need to write a loop for int e equals 0, e less 5, or n, sorry, and e plus plus, and we just writing result. Result equals 0, and after this we just writing we're adding to the result n dot I. Oh, not n, or and here, of course, if you have the result 0, you will get the 0. It's bad because you need to add as a 1. And here maybe we'll get factorial. If you don't know what is it factorial, it's like when you see some 5 factorial, for example, that means you need to write 5 dot multiplies by 2 by 3 by 1. And here you will get your result, it's 120, I think. 4 multiplies 4, 20, 60, 120. And here we need to return result. And here we call the forward thinking. Forward thinking, we calling function f5, for example. And I will add also backward thinking. Backward thinking, and here we add later some result. Backward, forward. Okay, we try to run the forward thinking first. We need maybe to add new line. Oh, sorry, backslash new line. Maybe we add uppercase, it's much fancier. Forward thinking, backward thinking, yes. When you're running, we get the result. Forward thinking 120, backward thinking there is no at the moment. And when you have like this implementation and using recursion, you're able to solve in different way. Factorial and n. And I will show two different implementation using the ternary operator and without the ternary operator. Without, you need to write the base case when the n equals 0. You need to return 1 because 0 factorial is 1. 0 factorial it equals 1. And else we doing returning calling itself factorial n minus 1 like backward thinking and multiplying by n. And here is as you see, the same amount of code we need to write, but we wasting the memory. And some good compilers by default, when see the recursion, maybe optimized and make as an iterative way if you have the linear recursion. But not all compilers do that. But sometimes the recursion, it's changed by the compiler how to execute because it wastes a lot of memory. And now we try only to call this function and to see the result, factorial 5. we got the same result, but here is a different approach. And maybe I write down here how it works. And I need to take some pen to write how it works. Oh, sorry, I hide this toolbar. Okay, now it's okay. First call, if we have n equals 5, you calling from the down. I write as f, because factorial is too long word. When you have s5, you calling the function. N equals 0. No, you're just calling the return factorial n minus 1, like f4 multiplies by n. N at the moment is 5. Then you're moving f4 equals f3 multiplies 5. Sorry for my writings. f3 equals f2 plus 5. f2 equals f1 plus 5. f1 equals n2, multiplies, sorry. And I made some mistakes, sorry. Maybe I delete this. First call, f5 equals f4 multiplies by n for a moment is 5. Then you multiplies by 4, by 3, by 2, by 1. And you're repeating this step till the top. And when you get the n0, you will get the 1. And you're moving down, 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 and multiplying by 5, you will get the result. The same like the backward thinking like do before. Like you need to write only the f4 equals f3 multiplies 5. f3 equals f2 multiplied by 5. f2 f1 multiplied by 5, and when you have the 1 equals f0 multiplied by 5, and f0 is equals 1. And when you have the 1, you just move this one here and remove from stack. After this, remove from stack. You will get the 5. 1 multiplies 5, it's 5. And then you're moving this here. 5 multiplies 5. You will get 25. Oh, sorry, not 5. My bad. 5, 4, 3, 2, 1. 5, 4, 5, 3, 1. Yes. And here you want 1, you will get 1. Here you will get 2. And I make some mess around here. Sorry, first time writing using this stuff. Maybe we need to delete this and this here. And here's okay. Okay, then we add in here multiplying by 4, by 3, by 2, by 1. And when you multiply here, first moving from the top, you will get the 1. Adding here, you will get result 1. Removing from stack, of course, before this moving here, 1 multiplies equals 2. Removing from stack, 2 adding here, 2 times 3 is 6. Removing from stack, adding here, 6 multiplies 4, 24. Removing from stack, and this result adding here. 24 multiplies 5 equals 120. Oh, 120, sorry. Removing from stack. And you get return here. That's it. It's working like this. And when you need to write a shorter way, this stuff, you will able to write like this. Remove this. Using the ternary operator, you're able to write like this. First you write n equals 0, a question mark, and here if true you write 1, else you write factorial itself. That's it. When you need a recursive call, you're able to write like this. It's much simpler way to write the recursive thinking, and we try to run it. We will get the same. Okay, then. That's it for this. We look into the factorial. And now we need to move into deeper. There is some tail recursive functions. Tail recursive is a form of linear recursion. In tail recursion, the recursive call is the last thing the function does. Often the value of recursive call is returned. As such, a tail recursive function can often be easily implemented in an iterative manner. By taking out the recursive call and replacing it with a loop, the same effect can generally be achieved. In fact, a good compiler can recognize tail recursion and convert it to iteration in order to optimize the performance of its code. And here, as you see, we'll get some example of tail recursion to calculate greatest common divisor of two numbers. If you have some greatest common divisor or GCD function and two parameters mm, you calling your you calling the function here. You're calling returning first recursive call here, and you get some result. If you get some result, if n less than m, you will get call itself that function. Else you calculating this function. Like you will get some, I don't know, result. Later you check this, if not get r equals 0, you're not returning n, you're calling the recursion here. And those two calls means that it's tail itself to the recursion. Because sometimes this function calls first here, because this not call, but this one is calling here, and you will get the call this first, and moving here it's through here, calling this, calling here, and here it's make a tail recursive function. Here it's, I don't know, it's hard to more explain, because tail recursive function is really this simple. It's when you have some more than once you're calling the same function, same function. Because if n less than this, you return the call itself. And later you checking the another condition, and if this condition happens, you will get the call itself with different parameters. And here it's tail recursive function. And there is, of course, the more interesting, the nonlinear recursive calls, when you have some binary recursive. Some recursive functions then just have one call to themselves. They have two or more functions with two recursive calls, are referred as binary recursive. Like when you have some trees, it's a good example how it looks like. The combination of mathematical combinations operation is a good example of function that can quickly be implemented a binary recursive function. The number of combinations often represented as nck, where we are chosen n elements out of set. And you're able to implement this cnk, and if you know combinatorics, you will get the binary recursive function, because you're calling twice. First, you're calling here plus here. And when you have the function, you need to like choose, of course, you have one. And when you're solving this, or just, I don't know, maybe you, I try to delete. You will get the structure. I don't want to solve, because you get this choose function call if is false, for example. This also divides into the two branches, like choose, and you need to calculate like this. You have one, it separates in two, and later if false, also when moving, if false when, and you just deeper, like a tree, binary recursive here. And as you see here, we move into more details and move to the next slides. I need to see that it's okay here. And if you have some questions, able to ask those questions. When we have the binary recursive, you have that like a tree structure. And Fibonacci number to sum up first four numbers, like when you have some numbers in Fibonacci 0, 1, 1, 2. If you would like to add those numbers from that sequence, you need to write a recursive function with a binary recursive, because you have the f1 call plus f another call. Like if you have, for example, we have fib3, yes, if we have n equals 3, we just call f3 equals fib. Oh, sorry, we don't write now. We just look into the table, it's better to see. First we call, if n equals 3, we call the fib2 and fib1. Now we're moving fib2, fib1 plus fib0. Then you need to make the branch fib1 equals 1 and fib0 is equals 0, because returning the n in base case. And when you have the fib and 0 and 1, you just in fib2 adding the 1 plus 0 is 1, and you adding here 1 instead into 2 will get 2. And the difference between this, you need to write like f3. It's dividing into parts, like n minus 1 f2 and f1. Here you will get f2, we'll have f1 and f0. And if you have f1 is result 1, result 0. And like this you will have some tree. And the tree structure, and because you have two branches, like left, right, left, right, left, right, etc. And you need to calculate like this in the table. For a moment it's easier to understand because you're call stack here and moving forward. And now we're moving to exponential recursive. Exponential recursive function is one that if you to draw out representation of all the function calls would have some exponential size. Better do not print out some recursive calls. And there is some functions which is exponentially grows, and if you're printing out, it's really hard to get some nice output. And in more details, we will find some exponential recursive function. Example. We have the print array function. Print array function printing our recursive function output. And print array, we have print permutations. As you see, we swapping elements, and after this printing and also swapping again those elements. And each time we print it. And if you have the huge n, you will get really grows fast function. I'm just later will show some different examples and you will see the difference. And the most interesting example is nested recursion. In nested recursion, one of the arguments to the recursive function is the recursive function itself. These functions tend to grow extremely fast, and a good example is a classical mathematical function, Ackermann function. It grows very quickly even for small values of x and y. You will get Ackermann is extremely large and cannot be computed with only definite iteration. A completely defined for loop, for example. It requires indefinite iteration, recursion, for example. And yeah, and if you would like to have more fun, try to calculate this function using your paper and write down this function output. Because when you have this Ackermann function, you have mn. If m equals 0, you're returning n plus 1. Else if you have return Ackermann call. And here is, as you see, nested calling. In the function, you're calling another function, Ackermann. It's like nested here. And for that purpose, if you have the nested calling, you will get really bad day for your calculations, because if you try yourself, you write down, it's not possible to try it using 4 and 2. If using 2 and 3, it's possible to calculate. And now we write down this function in the CLion. Okay, we need to switch to the C. We remove this. We just need to open CLion. Forget we need to pick here. And we write our Ackermann function. Int Ackermann, then int n. If m equals 0, returning n plus 1. Else if m equals 0, returning Ackermann m minus 1, 1. 1, 1. And else return Ackermann. First parameter will be m minus 1. And another parameter will be Ackermann call itself, inside the calling itself, m n minus 1. N minus 1. Okay. And we have the small function, and it's really, you see the calculations. If you would like to calculate something here. Okay, man. Calling Ackermann to 3, for example. Yeah, it's calculate fast, yeah? That's nothing special here. But if you're adding m is 4, thus we have the results. As you see here, we got stuck. I don't know it's any changes. Oh, we got, let's go down and we got the exit code. As you see, not possible to calculate using the small m, it's only 4. And if you see in Google, Ackermann function, you will see the result. The function is here. And here we see if you have 1, 2, you need only that many write down to the paper. If you have 4 and 3, you see how it's extremely fast growing. And you see 2 power 2 and power 65,000, etc. And if you see in the table, you see a lot of strange symbols, and it's really with some small numbers it's possible to call it, but if you have the 4, 3, it's not possible to calculate, and you will get the error or stack overflow. Here is nested recursive functions, and if you using recursion, it's really bad. Not a bad practice, but you need to think or write down on the paper to see it's possible to call to calculate, or use only the functions which is given by mathematicians and have proofs. When you see here, you will see the some explanation why it grows so fast and you're not able to calculate. And now we move into more detail. There's some slides left, and after this we end our stream. Okay, I need now move forward. Mutual recursive. As we see, we have only 2 types, linear and non-linear. It's subtypes. Mutual recursive. Function doesn't necessarily need to call itself. Some recursive functions work in the pairs or even larger groups. For example, function A calls B, which calls function C. In turns call function A. When you have a lot of chain of functions, you will get a mutual recursive, because doesn't need to be recursive, but you it make using the function chains. And of course, I show a simple example. When you have some is even number and is odd number. And as you see here, there is no call itself, but those function calling itself, not itself calling another function, which is calling another function. It's like ball effect, like when throwing ball and this throwing back. And it's even passing number, else return is odd and -1, as you see. We passing 3, for example, we returning this is odd 2. And is not even, we calling is even. And well, if this number is more, we are calling this again. And here it's really similar to recursive way, because you're calling as a recursive. And I have only 2 examples left. Now I will show some, maybe show normal without a graphical representation. We have some recursion. We have some simple generates all passwords. If you need to generate some sequence, for example, you need to generate if you need to generate simple sequence, like you have the characters A, B, C, or you have 1, 0, 1, doesn't matter. And if you have ABC, you would like to generate A, then AA, AB, BA, and etc. And without recursion, it's really not so easy to do like this, but you also possible to do. With recursion, you're able to do this. And here you will see that we have the char array, have int I is from another function, it's like mutual recursive. As you see before, it's not necessarily is the mutual recursive. I'm not sure, because this function, it's only there is two types, it's linear or non-linear. But mutual recursive, it's only from the community term, doesn't matter. Here you're calling another function, passing the index from another function. Here is a holder for the string, and here is the length of the array. Because in C language you need to calculate the length. And here we will have the base case, and when we have the base case and we get index 0, we will printing out the symbol, for example A, or any, doesn't matter which type of value. Here you will printing out, or A, B, C, doesn't matter when you reach the base case. And here you see as a for yacht, for J, because we have the outside for E loop outside. It's easier to use using the outside function to call recursively later here. And this for loop needs only for the characters. If you have one, you just calling one. If you have two charts, you call through the 3 columns or 4 columns, or doesn't matter if you have D, 5. Here it's like only for character length. Moving here, and here you are appending your sequence. If you have one, you are appending one. If you have more, you are appending more symbols. That line. And here calling itself, the function calling itself till the reach the I equals 0. If you're passing I is 3, you move 1, try minus 2, etc. Here is our converge to the base case, because doesn't matter. You first need to know which value you're passing. If you're passing 0, you will get the printing out instantly this symbol, and the symbol will be the first symbol you are passing from the array, like A. Yes. If the E is 1, you will get more symbols. If 2, 4 more. And here a basic idea is to get first or 2 symbols print, 1 or 2 or 3 or etc. And here you get the crack function. In the crack function, you will get the same array, passing like ABC or any character symbols, length of array, and we just iterating through that array, and we passing this to our recursive function. Like we passing our array A, B, and C, for example, and array length and index. First time we passing, we need the red marker. Sorry, I need to take some stuff. Okay. Here you need to pass I1. Here 0 not we don't need a 0, we need 1. Because if you're passing the 0, we'll get the printing instantly and get base case. And first we're passing 1. And when you're passing 1, you moving here 1. You're passing 1, and if 1 you're moving here. You have the array, and you get I is 1. Where is the I using here? You will get array yet you just printing the symbol, and later get your like first call you will get A, second call will be A, or not, maybe A, B, C, A, B, A, C, B, A, B, C, and etc. You will get that result. And here are some example how to create the passwords. Like later, I will add those examples how to use it, and you look into these examples. Maybe it's much easier to understand how it works. But here you're calling itself, and here you just have the crack function. And when you're running, you will get the output of the recursive way, like ABC, ABC, and example. Here you will get all permutations, like all possible combinations of your 3 letters. If you have the more letters, you're able to edit more. D. And I recommend it to try to implement using without recursion the same and see is it easier to use recursion or not recursive way. And of course, if you're adding more, like I don't know, more symbols, E, F. Don't forget, if you have like more, you're able to get the Stack Overflow and etc. G, T, Y. No, maybe it's enough. I mean, of course, output to the console, it's really not a great idea because you need to wait a lot of time. Better to output to the file. It's more faster, you will get the faster results. And here we will get the all possible combination of those symbols. And here we'll find the usage of the recursion also. And if you see the recursion into Google, you will find a lot of nice structure like this. Recursion, you'll find fractals like 2 branches of 3, Sierpinski triangle to divide in smaller problems and display. And there is more, I don't know, the images here like structures. Of course, a lot of algorithms using the recursion. And I have the example with that rectangles, and here's how to calculate sum. And of course, if you're able to solve the problem without recursion, and it's really easier to solve, better use the iterative way instead of recursion. Because as you see, you have a lot of the memory waste, or if memory is not important, you use the recursion. And if you would like to get Stack Overflow, use recursion. If you don't want to get Stack Overflow, don't use the recursion. And now I try to move more details. I, for our example, use the SFML C++ graphics lib. It's like an engine. It's better use instead of OpenGL. It's easier and have more documentation. Able to download here if you would like to create some, I don't know, mini game or some using the graphics, or just really nice lib. And of course you need to download concrete compiler for this, and compiler and version of FSML environment. And here recursive rectangle draw. Because I show only the console version, I would like to show in graphical way how to draw recursively. And of course I don't draw the snowflakes, I'm just draw some rectangles. And using this library, it's really easy to draw. You need to create a recursive draw function. And here is the render target. It's window, our window where we're putting the rectangles. We have float x, float y, and we have float width and height. Width and height is for the window size, so here is for rectangle. And when you're creating rectangle, you're passing only the x and y here, and we just rectangle added color, outline color, thickness, position. And position why we need, because we need to scaling down this. And for me, scaling down, of course, we're able to use the different function. I use the simple approach like dividing by 2 and dividing by 2. I getting the size of window minus rectangle half size if you need to get to the center, and y also using the same formula. Of course, you're able to use the different approach to add this rectangle. And here target draw function is drawing the rectangle, and the main place for our recursive draw is if you have x more than 0, you recursively draw the triangle, like drawing this. Of course, you're able to add base case different way, but here it's our implementation also able to do like in the if statement, if more or equals 0, you recursively draw the rectangle. And here, when you have the SFML library, you always need to have the main loop. It's in this library, it means the game loop or main loop. It really doesn't matter. Game loop when you have the loop where it's all rendering happens, rendering graphics. And here you're able to add a window size. You're able to add set frame limit. 60, for example, frames per second. You're able to, window is open. Here is a game loop and main loop when Windows is open. Yeah, it's every time is open. You have the events. Poll event means when you have some mouse, keyboard events, or any events of the window. And for example, at the moment we have event type close. When you hit the close this, you close the window. We clearing the window and we calling the recursive draw into the window our rectangle and the window size, and we display this drawing, and we get the drawing. And here it's also fractal examples. Before I show that example, this one, how it look in real project. Here it's some fractals. It's using the recursive functions. Mandelbrot, as you see, it's 19075. In computer graphics, you will get this nice drawing. Be able to draw the branches, and recursion, you're able to have some implementation of factorial. And factorial, it's, as you see here, how to calculate. Be able to draw the recursive circles like offsets. And here is a formula how to do this. And be able to draw a circle twice. And when you're drawing twice, you will get nice pattern, as you see here, for the recursion. And if you have some more than twice, you're calling 4 times, but you have different pattern, you will able to recursion 4 times, and you will get some nice pattern. Counter set is when you need to create like this lines, like a huge line, like a tree, as you see, divide, counter set. And here you counter set as different models, you're able to display like this. And also you're able to draw like this, those stars. And monster lines. And snowflakes, Sierpinski triangle, you're able to do like this, you're able to draw a tree like that. And there is a lot of nice structure how to draw it. Trees, different trees, computer graphics, really nice stuff you're able to do. Like that type tree. Alphabet, if you would like to create some strange sequences. You have nicer looking trees, and etc. Here are the fractals. Fractals, it's really nature oriented stuff. Okay, the final example for our today goal is to run it for open recursion. Start, maybe that one. Yeah, I have that one. And here I use our SFML graphics. You need only a single dependency using name SF. If you don't want to use SF, you just adding username space. If you're adding SF, you don't need to add this. Here we have the recursive draw, render target, rectangle, as you saw before in the slides, recursive draw, and that's it. Here is a function to draw our rectangles. And when you're running, you're getting the rectangles recursively. As you see, when you're going, not changing. And here, as you see, we'll get huge, and you down till the end. And you will get the nice pattern of rectangles. And I have a different implementation, but it's really not any recursive function. I'm just random function creating. Here I have some circle shape, and set radius, and just calling itself twice. And when I call it twice, I will get some results, strange results. The recursion working like strange. As you see, I get the huge circle, doesn't see here, and smaller, I don't know, here it's eyes or some pattern. When you're using recursion, you will get some really strange stuff. If you need to add more strangeness here, adding more road cycle, sorry, radius, if we multiply here, I'm not sure, I'm just doing anything here. I try to see. Is it crashing? Yep. Oh. I think we got some smaller shapes here. Just leaving plus radius 4 and divide by 4 and see what's happening here. Okay. Just some drawings up here maybe. And if we move those two, we will get our circle, like the eye, as you see here. If you need to draw some eye, you're able to do that function. Not sure which type of function we need maybe to fix a bit and change some parameters, but able to draw some eye or any figure. And here I recommended this library for you. If you learn, if you're creating the first programming practice, for the end I show you what you will need to do. At the moment, you need to enter the first programming practice. There is no anything here, but later I will add some information. You need to create some game in which you need to add some inventory, some HUD, and you need to create a mini game using the console, but to be able to use the graphical lib, it's really fun to use this library. It's easy to use it and easy to draw some sprites, like the moving frames and etc. If you would like, you're able to use also this library, and I recommended this library for your graphics without any OpenGL knowledge. You're able to use this library because it's easier to draw, easier to use it. Don't need to add yourself game loop. There is implemented already a game loop. You need to use only this code to have game loop and to have the events of keyboard and mouse and etc. And okay, thank you for today who's watching, and if you have any questions from the recursion, and recursion, it's only idea how to able to think, and it's not maybe in a lot of problems, when you're solving a lot of problems, you never use the recursion, but in the other person which is using the recursion, you need to understand how it works. If you have another project or you have the teammate which is using the recursion, you need to understand how it's thinking and how to work with recursion. And if you need to draw some fractals or to use some algorithms, or if you're solving some sorting, searching using the recursion, because there is some effective ways to use the recursion, you need to know what does it recursion. And if you have the questions, write comments or write email or any other techniques to ask for the questions. And thank you for attention, and see you in the next course.